Hey there, fellow Earth enthusiasts. Today, we're diving deep into a fascinating chapter from our planet's history, where a massive volcanic eruption turned ancient oceans deadly. Around 113 million years ago, the oceans faced a crisis that affected the tiniest of creatures, the plankton. But what does this have to do with us today? Let's find out. First things first, imagine a world where the tiniest, shelled plankton near the ocean surface suddenly started dying out. Their shells became smaller and thinner, and many species disappeared from the fossil record. Now, here's the interesting part: while these tiny creatures were struggling, their close relatives living on the seafloor came through the same stretch almost unchanged. So, what happened to the plankton? Well, it turns out they stopped growing shells. Now, let's talk about planktic foraminifera, tiny single-celled organisms that drift through the upper ocean and build shells from calcium carbonate. These tiny creatures are crucial, as they account for up to half of the calcium carbonate produced by marine life each year. But what makes this story even more intriguing is the fact that the shells of these plankton got smaller. And here's where it gets really interesting: the Albian shells held far more of the heavy calcium isotope than the Aptian shells. Now, you might be wondering, what does this have to do with volcanic eruptions? Well, it turns out that the carbon dioxide likely came from the Kerguelen Plateau, a volcanic province the size of a small continent in the southern Indian Ocean. The eruptions were so massive that they released gas into the air, which eventually reached the ocean, turning it acidic. But here's the catch: the surface ocean turned acidic first, while the deep water remained relatively unaffected for a while. Now, here's where it gets really fascinating: the plankton shells get smaller, and fewer species remain. The same stretch of rock holds the second largest die-off in this group's history. But why did the seafloor escape relatively unscathed? Well, it turns out that the dying plankton above them were the reason. When surface plankton sharply reduced their shell building, more alkalinity remained in the water, eventually circulating downward and providing additional buffering capacity for the deep ocean. Now, here's where it gets really relevant to today's world. Ocean chemistry is changing again, and the surface ocean has already crossed a threshold that researchers had set as a limit. And here's the scary part: acidity has risen by about 30% in the past 200 years. So, what does this mean for us? Well, it turns out that more research is needed to quantitatively compare Paleo-ocean acidification to modern-day ocean acidification. But here's the silver lining: Chen's team is already running measurements at other extinction intervals, including the one where the dinosaurs died. And guess what? Their records appear strikingly similar to the one documented for the Aptian/Albian ocean acidification event. So, if that holds up, the asteroid hit an ocean that was already in trouble. But here's the real takeaway: this story is a reminder of the delicate balance of our planet's ecosystems and the impact that volcanic eruptions can have on the oceans. So, there you have it, folks. A massive volcanic eruption turned ancient oceans deadly, and it's a story that's still relevant today. Stay curious, and keep exploring the wonders of our planet.